And if
Yes,
you
sir.
want to, after the finishing the first two part, so I think I'm also available. So for the first lecture about H-Infinity controller.
So in the first half, you will deliver this H infinity, or in the second half?
In the second
Uh,
half, in the second.
Second half. At what time, sir?
Uh, it depends on you because my meeting start in the afternoon Italian time, but it depends on we can follow your schedule, and then the first part I can be participating, but the second part I think you arrange it that the topic is related to okay about the time delay. So I think for lecture 11, so it's okay for me. Then, but of course, if the other colleague want also to contribute, it's also fine with me. But yes,
Actually, sir, Dr. Prajapati was asked before for this H infinity control. And as I mentioned you that he has agreed to deliver that talk.
okay,
But
yes, okay. We can if he's available, we
sir,
can he
what I
can.
request you, sir, in the first half, as your session is 10:30 to 12:30, so in the first half, if it is possible, you can deliver something on H infinity control from 12:30 to 1 p.m. Uh, Another 30 minutes you can extend, sir, 30-40 minutes.
Okay, okay. Up to 1 p.m. It's okay. Okay,
Okay, sir. Okay, sir.
no problem.
So I have requested the participants to join. Sir, it's 10:30 only. Uh, if you allow, we can wait for another minute, 1 or 2 minutes, and
Sure, sure.
let them
Okay,
join. Yeah.
okay. Thank you.
Okay, sir. We can start the sessions, and good morning to one and all again. And I again welcome our foreign experts, Professor Hamid Raza Karimi, sir. Uh, Day 4 of 1 week GAN course on resilient control of cyber physical systems. Uh, in this today's first hub sessions, Sir is going to deliver his talk on cyber attacks, event-based fault-tolerant control, and brief introductions followed by the applications of H-infinity control. So with this, I request respected Sir to please continue the sessions.
Okay, thank you very much. Good morning, everyone. So let's continue our lecture on the topic of the cybersecurity. So basically for today, I want to talk about two particular issues. So one issue is about the effect of the cyber attack. Basically, we call it as a measurement outliers. So in some application to the CPS and also the mobile, such as mobile robot. And then I will talk about some new technology we have for the fusion estimation for enhancing this mobile robot localization under all of these features. But this presentation today, so that first I'm going to give an introduction to the topic. So because this is a very interesting topic for research and industry. Another side, if we look at some application to the autonomous cars or autonomous vehicles, and we can see that there is some standards basically for the enhancing the safety and security as we discussed yesterday. So yesterday we discussed some standards that we have basically for the autonomous driving. And for this particular case, so SAE J3016 is about the level of automated driving. So if we look at the level of the driving from the no automation, level zeros, to level 1 is a driver assistant, level 2 is a partial automation. So now you can see that the system support you during the driving. But nowadays, the technology moves on to the full automation. It means the conditional automation, high automation, and also the full automation to level 5. So if we want to enhance this kind of the autonomy in the automated driving, so one challenge is about the safety and also some issues we have about the measurement. Because important issues in the cyber attacks and cyber security is the malfunction of your sensor data. And if the sensor data is under cyber attack, so how we can guarantee the safety of the autonomous automated driving. And the challenging part is focusing on some outliers. Outliers on the sensor data include the fault, includes the attacks, and not the sensor should be able, basically the system should be able to handle this kind of the misinformation we have from the sensor data. So now we can see that the topic is very challenging. Another topic, if we look at the sensor data, because in this particular application, so you need to look at in order to precise a vehicle direct environment object detection sensor can be used. So in this particular case, so if we look at basically some distinction between the two sets of a sensor. So we have a passive sensors. It means that you can detect existing energy like light or radiation. So these passive sensors are reflecting from the object in the environment. So the passive sensor could be like a CCTV camera or CMOS camera. So that's it. These are the passive sensors. We have another sensor as active sensors. So this kind of the sensors, they send some signal, for example, electromagnetic signal, and then and receive or sense its reflection. So from the sending and also the receiving the signal, so such as the ultrasonic sensor or the radar, so we can basically look at as the sense of the information. So now you can see that the one CPS system, like a car, consists of the many sensor technology mounted on the cars, including the passive sensors, active sensors, and now you can see that each sensor has a particular coverage. So in for this case, so we can see that more sensors, more information, but at the same time, there could be more threats, basically to the sensor data. So now today I'm going to tell you that if you have such a, for example, particular sensor, like the active sensor, like the LiDAR, so how you are able to handle the cyber security. So in your sensor data, and then the car itself can, or the robot itself, it can find a good localization. If the robot or the car can have a good localization with the systems under control, because you can follow the same automated driving. So regarding to the sensor, so basically this could be the one spectrogram of the signal, so based on the wavelength. So now you can see that the different sensor has a different wavelength. So for example, a passive sensor or active sensors, and this kind of basically the spectrum of the signal based on electromagnetic spectrum, it can be used for the perceptual sensors. But this could be the same active sensor. You can see that this here, the sensor can send out, the signal can be sent out, like electromagnetic signal, and then after the hitting on the barrier, the signal can be reflected to the source. So this kind of a transition of the signal, so basically you can calculate one parameter is a time of flight. So the time of flight, you can see the time of flight principle, TOF. So it's one of the key parameter for the sensor, for the active sensor, in order to calculate the distance from the object. Okay, so if the landmark or this point can be detected, the distance can be detected, and then the car can try to consider it to avoid any collision, and therefore this active sensor principle, it works in such a way. So the sensing, the data, it is the main issue we have in this kind of the large scale system. So because in the autonomous cars, so the basically you have maybe partly or even the environment is unknown, and environment is dynamic. So now in this unknown or the dynamic environment, so it's very important to simultaneously is to build a map of this environment mapping, and also how the robot or the car can localize itself within the map. So now you can see that the environment mapping and localization is the important aspect. So for the basically the autonomous cars. So the input to perform this simultaneous localization and mapping is the SLAM. So in robotics, so you heard about a SLAM, a keyword. A SLAM is a simultaneous localization and the mapping. So and in this particular case, so you need to look at your sensor data. And then if there is some existing or the pre-existing maps, it may be created by the AI or the human. So you can combine so your sensor data and also pre-existing information. So this could be one unknown environment. You can see, so in this unknown or uncertain environment, there are different cars, human, and then you can see that if the car want to find the position, the location based on a SLAM, so this environment is a challenging, and therefore there could be difficulties for to find the precise localization. But anyway, so the sensor on the cars, So they can check it out, basically all basically the safety issues in order to avoid the collision. And then the task is that if your sensors is containing some false information, so how you can still guarantee basically the automated driving for these particular cars. But now you can see that for the high technology, so it's very complex. So it's such a complex environment. So to realize that this higher autonomy level, and therefore, how to enhance it? First, we need to come back to the data, to the sensor data. And therefore, you need to have a better technology to do the data processing. And therefore, today I'm trying to give a little bit more in the favor of the data in order to do the better estimation of the position of the vehicles. So the position measurements are mainly influenced by the odometry. It means that you can get the position data from the wheel sensors. It's the odometry data information, or you can use the data reckoning. Data reckoning means that you can use some heading sensors. If you are using the heading sensors, so basically, or you can combine the odometry and the reckoning sensors. So the movement of the robot, it means because of this movement, first we can get some data from the wheels. So based on encoded data, and also then you can also use some data from the heading sensors. So the heading sensor, like this information is useful for the rotation. Okay, now you have a position, and also for the other information such as the heading sensors. So then you can also combine or you can integrate it for the position estimation. So this approach, if you want to use it, the data from the views, so it's a very straightforward, it's very easy. But the problem is that, so the wheel sensor data for the cars is it could be, there could be the errors in the calculation, and also could become the unbounded if you have some attacks on the sensor data from the wheel. So now you can see that for the vehicle and the robot, if you are using the sensor data from the wheels for the control and the positioning, if there is some cyber security, so the result is not accurate, and even you cannot get any the basic estimation of the position of the car. So this is the reason that the problem of the cybersecurity for the cars is very important. So therefore, we need to find a better technology, better solution for the higher safety. So now you can use another sensor, like a heading sensor. So this heading sensor, like a gyroscope. So this sensor can help to reduce the accumulated errors. But the main problem still remains. But this sentence is very important. Even if you are using another sensor like a gyroscope in the vehicle or the robot, so the problem cannot be solved, because if there is any attacks to the cars, specifically to the sensor, wheel sensors, so all of your information is not able to give you the precise the localization of the vehicle, and this problem is still remains. So this problem is a big problem. So for the higher automated autonomy in the autonomous driving. So now my presentation today, so I try to tell you the problem and why this kind of issues is important from application, and at least I show you some solution how to solve this kind of problem. So let's look at the odometry data. Odometry data, so if you look at this car with the two wheels, so now you can see that the car in the position X, in the direction X, and the direction Y, so there is some position X and Y. At the same time, so this car has a velocity V. You can see the velocity v. At the same time, there is some angular velocity, the omega, because of the rotation of the wheels. Okay, so this car, so it has the direct movement, and also there is an orientation, the alpha, because of the rotation of the car. So now based on this information from the wheel information, if you know the speed of the linear speed of the wheel with the VR, and also rotational speed, the omega r, then you need also to look at the alpha. The alpha is the orientation. So if you write down the kinematics, so for this you can, I will show you the next. So in this scenario, there are some errors in your calculations. So the error source could be some deterministic errors. So deterministic errors can be eliminated by the calibration. So if you do the sensor calibration, you can remove some deterministic errors. But what about the non-deterministic errors? So it also could be described by the error in the modeling, and always they give some uncertain estimation. So this is a two type of the error you have in this modeling. But the major error source, so the major sources for the error in your modeling, so could be some limited resolution field integration. Because if you are using the time integration, so based on your sensor data, for example, if you go from the velocity to the position, you are doing some integration, right? So in this integration, there could be some bias in the calculation of the position. So mechanical problem, misalignment of the wheels. So this misalignment of the wheels for the wheels left and right, they can give you some deterministic errors. So unequal wheel diameter. So if the diameter of the wheel are not equal, it can also give some deterministics. There could be some variation in the context of the point of the wheel, and so on. So now you can see that there are some major errors. If it goes to some sort of mechanical errors, it can be solved. But if you have some fundamental errors from the computation and also from the sensor data, it's difficult, and therefore you need to pay very carefully. So one of the sensor is useful for the autonomous driving. So it's related to basically to the LiDAR. So basically there could be some advantages. So this kind of the Doppler radar sensors, the advantage is the greater coverage, lower cost, a smaller size, and also lower weight. But there could be some advantage for the Doppler radar sensors. So this radar sensor is widely used in intelligent transportation, space exploration, and also wireless communication. And there is a significant application in mobile robot localization. So we can use a Doppler radar sensor for the estimation, position, and also the heading of the mobile robot. And you can use the information, we call it the Doppler frequency shift measurement information. So the Doppler frequency shift is basically the information you can get from the Doppler radar sensors. And this information, you can combine a feature-based mapping with the landmark, and you can use the Doppler radar. You can do some extended Kalman filtering, and basically, and also there's some other filtering techniques. So now you can see that you can use some advanced estimation. So based on the information you have from the Doppler radar sensors, and even you can combine it with the feature-based mapping you have obtained. So basically based on some other techniques. Okay, so after this introduction, I want to talk about the localization based on some measurement outlier resistance on the network. So you see, so these outliers, so includes for example, the fault. If the sensor is faulty, as we discussed yesterday about the fault in the sensors. So it also could be the attacks. So the outlier, so it could be both. And the design should be resistance. Resistance is the topic of the lecture at the first day. If you remember that we discussed about the resilient control and the CPS, the cyber physical system should be resilient. So it means the resistance means the resilient. Outlier means attacks. It could be the, for example, the fault and all related to the data, the measurement. So now you can see that this sentence is a topic that they can cover what we are discussing up to now in this course. So let's talk about the robot. So I told you that the robot, let's assume that in the X and Y direction, you know the center of gravity X, the position of the robot. Another information, so another information could be the theta. So this information, so maybe I can also, okay. So this information, the theta is the orientation of the robot. And if you start to write the kinematics equation for this robot, you can write the velocity in the y direction, and also the rotational speed based on the omega and also the theta. So now you can see that the kinematics of the robot, it has the three information. One is the X and Y, another is the theta. The theta basically shows the orientation of basically the robot with respect to X and Y. But at the same time, so the information you have from the mobile robot, so it could be the YR, and also it could be the includes the velocity, the linear velocity v, and also the angular velocity, the omega. So it means that based on these two speed information, so you need to obtain x, y, and the theta, okay? So now the point is that this linear velocity v and the angular velocity omega, you can get this information. And based on this information, you need to obtain the position x, y, and also the theta is the rotation. So the first assumption is that the displacement and angular velocity of the mobile robot received by the odometric sensors are constant over the sampling time. So we assume that in one sampling time, this information of the displacement and also the two velocities you can obtain. So these are the basic, the constant. So in this case, you can linearize, you can be discretize. You can discretize the kinematics equation in the equation number 2, and the delta t is the sampling time, okay? So for one sampling time, you can write these to the discrete model for the position and also the angle based on the two velocities, linear velocity and also the angular velocities. But you can see that this model is nonlinear because here you have a sine and a cosine, and therefore this kinematics model is nonlinear. So if you start to represent it based on the input and output, you can take the vector x as a position x, y, and the theta, and also you can consider the control input or the input data is the sampling time multiplied velocity, linear velocity, and sampling time multiplied the angular velocity. It means that you have a U1 and U2 as the two information. So U1, U2 is the information, so you have it from the sensors. So in this case, so the system, the system number 2, it can be represented like this. So the system can be represented like xk plus 1 as a function f of the function of x and uk. And this function can be represented like this. fxu is the xk plus this term. Of course, you can see that this function f is nonlinear because of the sine and the cosine. But if you look at equation 3, in equation 3, So this is a nonlinear function, but you have some input data from the sensor, but you need to find x. And this is basically the challenging part, because for this challenging part, so you need to look at the accuracy of your sensor data, and therefore I'm going to talk about how to get a better estimation. But the first problem in estimation X is about the nonlinearity we have from the function f. Okay, so so if you want to avoid this nonlinearity, you can use the Taylor series expansion. So by using the Taylor series expansion to estimate x at k, so you can basically express equation 3 like this equation 4. In this equation 4, you have a discrete model for the xk, but you have a matrix ak. So this matrix ak, so it's a Jacobian matrix. So you can calculate ak by the partial derivative of the function f respect to x, and then if by calculating this partial derivative, but if you look at x could be equal estimation of the x, so you can basically write this equation. So this matrix you can find, so is you can see that the estimation of the theta will be appeared. So, and then you have a two input signal, and this could be gives you the matrix AK. Okay, so in this case, so if you put AK in this equation, the problem is the phi k. So if you want to have a good estimation, so this phi k is the error signal, and the phi k is a function f at the estimated signal x hat k minus the linear part. It's a nonlinear term minus the linear part, and also here there is an additional term as a rho k, represent the higher order terms of the Taylor series expansion. Okay, so if you are using the Taylor series expansion for the different degrees of the approximation, so you can expect to get some errors like this, like a 5K. Okay, so now the problem is about this, about the 5K, because the 5K, if there is attacks or if there is a fault, so this 5K can increase a lot, and therefore this become out of control. So we need to discuss about this more specifically. So what information we have? The information we have, as I told you before, the sensor is a Doppler radar sensors. So let's assume that the number of sensors is L. L Doppler radars, assume that is mounted on the robot. And then this L sensor, they can give you some sensor data. So the position, the point MI, it means the position X and Y in the Cartesian space, X and Y. So these are chosen as the landmarks of the some landmarks around of the robot. Okay, so you know that if you are talking about the autonomous mobile robot, so you should know that in environment there is a landmarks. So the landmarks is some specific position, a specific object with the some position MI. And it depends on you how many landmarks you want to choose. For example, here we have a L sensors. We are choosing the L landmark. It means that each landmarks so could be useful for to work with one sensor. So the landmarks just can be taken for the better orientation or the position of the robot in the environment. And then based on this information, the sensor can obtain from the position respect to the landmarks, the robot start to find the position itself. Okay, so now you have a sensors, you have a landmarks. So now you need to know what the data you get from the radar sensors. So the radar sensor, I told you that it gives you the Doppler frequency shift data. But the Doppler frequency shift means that the sensor number I, so they can give you the Doppler frequency shift and also the azimuth information. Okay, so two information. So the Doppler frequency shift and also the azimuth information from the landmark number I. So these two data, these are the two data you can get from each sensor, and each sensor find this particular information respect to the landmark number I, and therefore you have these two data. So if you want to see from the mathematics, so it means that at the time instant k, so you have a measure Doppler frequency shift, BIK, and also the azimuth information phi ik. So these two, the information from the landmark I, so we call the measurement. Okay, so now if you have some cyber security attacks, so these two information can be changed, can be manipulated, and therefore your estimation should be robust. How to get a robust estimation in order to avoid any problem, such a problem from the attacks is a very challenging topic. So now I want to talk about the sensor modeling. You know that you need to pay attention that if you are using the Doppler radar sensor, you need to develop the measurement model or the sensor model. So let's assume that for the sensor number I, for the radar number I, so the measurement is a Zi bar K. So this information is a nonlinear function of the two information. One is the position X and also the position of the landmarks for the MI, okay? Position of the robot and position of the landmark, and based on the function J, so you can find two information, BIK, a Doppler frequency shift, and phi ik is the azimuth information. Okay, so this is the reverse problem. This it means that you have BIK, phi ik. Now you need to find xk because the MI is given, but you don't have this. And therefore you need to find basically the estimation. So, but if you are using the Doppler radar sensors, so the function jxk mi, it can be represented like this. So this mathematical model you can see. So this is basically some expression. So you can write it down for the position of basically the robot or the vehicle respect to landmark number I. It means that this mathematical model can be written. In this mathematical model, you know that X and I, Y and I is the position of the landmarks. X and the theta and Y is the position of the robot in the basically for the case of the kinematics. And also there is some other parameters like FC, and this parameter is the radar carrier frequency, and the parameter C is the speed of the light. Okay, so this mathematical model, so it gives you the some relation between the sensor data and also the position you want to obtain. But please pay attention that this is a nonlinear function, and at any time you could get some wrong data, and then how to get the good estimation is a very big problem in the context of the automated mobile robot or the cars. Okay, so I want to tell you a little bit more about the sensor data. So the sensor data are, you know, is a nonlinear function J. So you can approximate it like this. So if you write down the sensor data like a linear term based on the Taylor series expansion, so you can find this basically the error sigma T psi ik, and this is a linear part. And the matrix CIK, so you can calculate it from this Taylor series expansion. You can see, you can take all the derivatives with respect to X, Y, and the theta. This is a Jacobian matrix at the estimated xk, x hat k. Okay, so if you calculate this partial derivative, I have written here all the partial derivatives. You can see all of this mathematical, you can calculate all the partial derivatives. There is a lot of the formulation. And then you have your sensor data. Now this is a problem. What is the problem? It's the measurement outliers. Measurement outliers in the cybersecurity is a first problem. So because in the practical application, if there is a sudden environment change or the sensor fault or the cyber attack, so this outlier can be produced. Okay, so now we know that why we are talking about the cyber security, why we are talking about the cyber attacks, because all of these things, they can change your data. And therefore, we call it the sensor or the measurement outliers. So the outlier is treated as a class of the impulsive and the bounded disturbance. Okay, so in this case, so we are treating these outliers as a bounded disturbance and also in impulsive form. So now you can see that the TSI-IK, so I introduced it from this expression. So TSI-IK was the approximation error based on the Taylor series expansion. It can be also used to express the linearization error, external noise, and also possible outliers. Okay, this is very important. If there is attacks or the fault in your data, in your sensors, all the information, it goes to TSI-IP. So now this term, so it's important term if you want to use it for the estimation, robustness estimated analysis. Okay, so to mitigate the network congestion, so we talk about CPS, cyber physical system, it contains the network. So one problem we discussed it during the course about the network congestion. If you want to mitigate the network congestion, so you can use basically some protocol like a RR. The RR protocol is a round robin protocol. This protocol is a very well-known protocol in the network control. So it can be used for the data scheduling. It means that you need to schedule the transmission of the data over the networks. Okay, so if you are using the RR protocol, now you need to see that the sensor data, ZI bar K. So this information or the sensor information is a Doppler radar measurement data received by estimator. So now what happened here? So your sensors receive the data from the landmarks, okay? So now the sensor data, it was ZI bar K. You see here I wrote ZI bar K, if you remember here. So ZI bar K is the sensor received at the radar sensor. But this data should be sent through the network, and therefore there is another data, is a ZI arrow K. So ZI arrow K is the sensor data has been received after the network by estimator. Okay, so there are two different data. So now if you are using the round robin protocol, so ZI arrow K, it can be sent in the periodical form. There is a function pi k. So this function pi k, it says that if you are following this mathematical form, it says that the pi k is a sensor obtaining the privilege to access the communication networks. It means that for the sensor number I can send at this particular time. So the data from the sensor number I to the estimator, and therefore there is such information. In other sampling time, there is no information. Why? Because you want to save the bandwidth. This was one of the reasons that in the event-based control, so you don't need to send all the data. So you can use some specific protocol, for example, like the RR protocol, not to send all the data, because if you send all the data, there could be a lot of problem about the congestion, limited bandwidth, and so on. Okay, so now based on equation number 7, you have particular data. So at the estimator, and this data can be used for estimation. So now you have two data. One is the Z bar K. These are the data at the sensor. Z arrow K is the sensor data at the estimator. And also so based on these two particular information, so based on this protocol of the network, you can write equation number 8. So equation number 8, it says that what is the relation between the sensor data at the estimator received by estimator. It has such a formulation respect to the sensor at the data and the data at the sensor level. So here there is such a make a function phi arrow pi k. So this is a function, and if you write it like this, so now you can see that these networks is very important because it affects on the data you can receive at estimator. At the same time, so these metrics, phi arrow pi k, it can be represented based on this diagonal matrix term, and also this term, as you noticed before, the T sign arrow K is represent the error in your estimation. So now I'm talking more about this part. Okay, so this is a mathematical model for the actual received data measurement at estimator. Okay, so in equation 8, in this equation, we can see that the ZIK is a useful measurement data to determine the desired estimator, and the other measurements are equal zeros. So this equation number 8 increases the dimension of the measurement data, and there is a lot of computational complexity. So this equation number 8 has some drawbacks in terms of computational complexity in the real-time mobile robot. Okay, so if you want to reduce the computational complexity, so you can follow equation number 9. So in equation number 9, so there could be some sort of the representation. So based on and to find the relation that is zk equals ck xk plus t psi k, and the ck it has such a representation. Okay, it means that you can include the information of the network in your two metrics C and also the new function T psi, and therefore this equation 9 it can be simplified in this form. So now we need to introduce our estimator. So estimator we are introducing for the basically the mobile robot localization problem under the RR protocol is this equation 10. So equation 10 is a nonlinear estimator. Why? Because x hat k plus 1 is ak x hat k. It is a time varying. And if you look at the right side, here is the LK multiplied the saturation of the sigma k zk minus z hat k. So here is very important. So now when we talk about dealing with the cyber security, you need to find this nonlinear estimator. So this is not linear, it's a saturation function respect to sigma k. Sigma k, I will introduce you later. So now you can see that this nonlinear estimation, so x hat k is the state estimation of xk at the time instant k. Lk is the estimator parameter to be determined. Is a sort of the estimator gain, observer gain. Another term is the function saturation sigma k is sk. So this saturation function, so there is a one variable sigma k. So it is a vector, is sigma 1, sigma 2. So sigma 1, sigma 2 is responsible to deal with the cyber attack, is responsible to deal with the measurement outliers. If the attack exists and this want to increase, so this function will be saturated, and then you can avoid any problem in the estimation. So the saturation function sigma k, it has a two levels, sigma 1, sigma 2. There are two functions like this. And I can tell you that the first term is responsible for the Doppler frequency shift data if there is an attack in the Doppler frequency shift. And sigma 2 is responsible to deal with the attacks on the azimuth information from the LiDAR sensor. Now you can see that the sigma 1, sigma 2, they are responsible for controlling some outliers like the attacks in your data. Okay, so this is a function. You have it, and the function is like this, and this is totally nonlinear estimator. Okay, so here again, the sigma k, I told you that there are the sigma k, so it's a variable saturation limit. It can be introduced like this. Sigma tau k is from this mathematical formulation, but please pay attention that the sigma is a time varying, and this sigma bar k is a time varying. It has a dynamics like equation 12. It means that the sigma bar k plus 1 is a lambda k sigma bar k plus this information. So now you can notice that this limit, the limit is a time varying, and depends on your data. If it's zk minus z bar k, it gives you some outliers like attacks, so the sigma k can be updated. Of course, there are some in a metric like rk or lambda k, and these two parameters you can choose it by yourself. Okay, by choosing this parameter, you can tune the sigma bar k in order to protect your estimation. Okay, so if you look at this mathematical model, you can see that the error signal is x minus x hat k. So this error signal, so it can be represented in the dynamical form ek plus 1 like equation 13a. Another equation is the evolution dynamics for the sigma k. Then you can write equation number 13b. But if you look at these two equations, it's very interesting that the vector qk, it contains the sigma k, and t side k is the outlier information, and also some term of the saturation function like this. So we take it in the vector qk. So the vector qk exists here in equation 13a, and also in equation 13b, you have this sigma k. So now this is a nonlinear function and also time varying. And then we need to think about how to make the convergence of this estimator. So there is some objective function in this design. The objective is to design a time varying state estimator in the form of the equation 10 I showed you before for the mobile robot system. So more specifically, we are interested in looking for the estimator parameter L, lambda, matrix R, matrix W, such that the aerodynamic system is satisfied the following performance. So this is a sort of the H infinity performance. So today there is also one course about the H infinity control, but this equation number 14 is a sort of the H infinity the condition for designing this estimator. What does it mean? It means that the effect of the T side K as a disturbance, so should be mitigated over the error signals by tuning the parameter the gamma. So if you choose the parameter gamma, you can see how much you can reduce the effect of the disturbance or the outliers over your error signal. Okay, so this performance should be satisfied, and you need to satisfy this performance index by choosing the parameter the gamma. And okay, so now there is one theorem. So this theorem says that if you have this mobile robot, and if you want to satisfy the H infinity disturbance attenuation, the gamma, And then if you have some estimated parameter like L, R, the omega, and also some other parameter lambda k, you remember that the RK is like the omega k and the lambda k are in the evolution dynamics, and the LK is the estimator gain. All this information you don't know it. You need to design it. You need to design these parameters. So you need to look at the aerodynamics. I showed you before aerodynamics for the state estimation and also for the evolution dynamics. So the H infinity performance condition should be satisfied. I showed you before it needs this H infinity condition. So this should be satisfied. So if there exists a family of the positive different matrices, if there is such a matrix, to the following the recursive LMI. LMI is a linear matrix inequality, but we have some recursive LMIs. So this should be satisfied. Matrix EK should be negative, and this is your matrix EK, okay? So this matrix should be negative, and this is the time varying. We have a recursive R, and this LMI is a linear matrix inequality. But each term is represented like this. I have written here. So this condition should be satisfied. How to solve it? So if you learn about H infinity condition, so there is a toolbox in MATLAB about the H infinity toolbox. So you can write the program for LMI, then you can solve it, and it's not so difficult. And then finally you can also satisfy this condition for the initial condition, and finally you can obtain the result. Okay, so the second part is this was about the satisfaction of the H infinity condition, but now I need to show you how to design the parameters, because you need to find basically the observer gain. So again, for the same strategy, there is another theorem. It says that if you solve this LMI problem number 16, so in this case, there is some LMI variables like the matrix PK, so the matrix K, matrix R, matrix W, and also the parameter the lambda. So if there exists this solution to this LMI, to this recursive LMI, so then you can obtain the LK. So now the conclusion is here. And the state estimator parameter lambda LK, you can calculate from this mathematical model. So this mathematical model, you can see that the LK, it can be calculated from the matrix P inverse multiplied K. So, both K and the matrix P, they are the solution of your LMI. It means LMI should be solved at each iteration. At each iteration, you can find a new L, because L is a time varying. And then you can design your time varying estimator. Okay, so there is an algorithm to solve this problem. First, we need to give some initial conditions. So like the HNT performance, the gamma I told you before. And there is some initial values for the LMI variables. And then you need to solve this LMI number 16 in the recursive form, and then to obtain all of this information. And then when you obtain this information, you can calculate L. I'll show you before. L is a P inverse multiplied K, okay? So then you can repeat it and repeat it basically to get the estimated values. Okay, so let's a little bit discuss about the case of without measurement outliers. So here I talk about the outliers like cybersecurity, but if there is no cybersecurity, a sigma goes to infinity. So if the sigma goes to infinity, it means that you don't have any attacks. So then you have seen in other courses. In other courses, when you design this estimator like a Kalman or a Leuenberger observer, if you avoid this saturation term, it means that you have this mathematical model. Mathematical model number 18 It means that the sigma goes to infinity just in the case of that there is no outliers. So, okay, and you know about this, and that's it. I can repeat it again. So for this particular case, you can also develop the error signal. You can develop the evolution dynamics for the error signal. And now you can see that there is no evolution for sigma because sigma is infinity, okay? But only you have this H infinity condition. This H infinity condition means that you need to satisfy or mitigate the energy of the disturbance over the error signal. So this problem is relatively simple because you can, there is no sigma. This is only the time value estimator. The same theorem, so you can adapt it for this case, but it is very similar what I proposed before. Now I want to show you some simulation result. Let's assume that we have a simulation for 300 sample for the horizon N samples. And then there are three Doppler radar sensors on the mobile robot. And then you can follow some sort of the profile. So let's assume that the robot should follow some particular position. For this sampling time, the speed should be 400, and also the angular velocity should be this. And for this time, the robot should follow the speed of the 400 and also this angular velocity. It means that we can give some particular set point. So the robot should track this information. So these are the initial conditions for this problem simulation. And this information, because you have a three sensors, then you have a three landmarks, N1, N2, N3. You see, all the information is given. And then you can start with the initial values for the evolution dynamics of the sigma k. And this is a starting point for your LMI, basically solving the LMI. Okay. So if you start and here the H infinity disturbance activation level, the gamma is this parameter, and because based on this parameter, you can basically find a feasible solution for the LMI you have. Okay, so these are some index function. So index function, if you want to see how much your result is accurate, you need to compare, you need to look at the error signal in this to the calculation. These are some Euclidean distance and also for the theta. So you need to measure this, you need to calculate this index function just to show that how much error you have in the calculation based on estimation and the real parameter. Okay, so based on this Euclidean function, you can write down the two error, mean error, so for the position and also for the angles, and you need to evaluate. So how much your estimator is robust, and this is something to show the accuracy of your result. Okay, so even you can use the maximum values of the ME and M theta. These are the two different index functions. You can choose both. You can choose the mean value, you can choose the maximum deviation, and both are okay. Depends on you if you want to do the better analysis of your result. Okay, so based on this table, you can see that if you have a noise or you have a noisy data in your file, okay, so basically in your estimation error, if represented with a different level of the noise, you can see that the error in the mean value and also the maximum values, so they also increase. If the noise increase, so now you can see that these error values also increase. And it means that the noise or the cyber attacks, they make a very important effect on your estimation part, on the error estimation. So these are the sum values for the parameter of the LMI variables, because if you solve the theorem by using the LMIs, at any iteration k, 1, 2, 3, and so on, for different time, you can find different metrics L for estimators and also other parameters for the LMI, okay? So you need to solve LMI at each iteration, but if you are not familiar with LMI, so I can provide you maybe some other lectures, or I can provide you some MATLAB code in order to solve this problem. But if you solve this problem, you can get all this information. And this is a picture about the actual mobile robot trajectory and its estimation. So now you can see that there are two curves, is the actual trajectory and also estimated. So you see that the red one is trying to follow the actual trajectories. And this is also the tracking of the actual, also respect to estimation for the angular, for the angle you can see for the theta, and you can follow the estimation. And the result is quite good. And because here we have the sigma value. The sigma values, it was you remember that it was has a two sigma 1, sigma 2. So the sigma 1 is for the measurement outliers. So for the frequency Doppler shift, and the sigma 2 is handling the outliers on the azimuth information. So now you can see that the both sigma 1, sigma 2 has such a profile, and they are active. You can see that there are some variation, mean the sigma, it works, and try to protect your estimators. So now I want to show you that if there's attacks, what will happen? Assume that at the time K90 and K280, so there could be some outliers in your data. So now you can model as a disturbance, as a noise, or as an impulse function. So now there could be such a problem at this time. So now you see that at the time 90 and 280, so now we can see that there are three plots. Blue line is the actual trajectory, red line is estimated based on the algorithm number 1, and the blue dash line is estimated based on algorithm number 2. So the algorithm number 1, it can handle basically the attacks. And then you can see that the red line, so it is very smooth. There is no any spikes. Red is very smooth, and they can follow the blue line. Why? Because in your mathematical estimator, you have used the sigma, and the sigma can control the deviation. But if you look at the black line, so the black line, the dashed line, is no any sigma. If you are using the regular estimator, then you can see that the attacks, they can change your position of the robot, and this is basically the problem. So now for the position, you can see at the time 90 and the time 280, there are two spikes. So these two spikes, because you didn't consider sigma. If you take the sigma, you can get the red signal. The red signal, it means more robust. And this is the reason that for the cybersecurity, you need to use some advanced estimator. An advanced estimator, one could be like this I presented today. So the same is also for the angles. For the angle, you can see that if you are not using the sigma, you can get these spikes. But the red signal, you can see there is no spikes, and therefore your estimation is quite. So now the sigma 1, sigma 2, they have such a behavior. Exactly, you can see that at the time 90 and 270, so these two spikes in the sigma, they are responsible to control the attacks. And this is a reason that you need to pay attention to look at this problem. Okay, I think there is no time to go to this part. Maybe of course, I can provide you this material, but I can stop at this point. So maybe we can have a 5 minutes break. If there is no question, we can have a 5 minutes break, and after break, we can continue to the second part. Any question? Okay, so if no question, so we can stop here, but I can provide you this material for fusion estimation. You can study by yourself, and if you have questions, you can contact me. But we can stop this part because we have another part for today. I want to present it after the 5 minutes break. Okay, we can meet in 5 minutes. Okay, thank you. Okay, so welcome back to the course. If there is no question, so I can start to go to the second part of the lecture today. So in the second part, I want to talk about some topics related to the HMPT control, basically for some application to the multi-agent systems. And also I will discuss about some effect of the event triggering control incorporation basically with the model predictive control and also for the multi-agent system. And also I will talk about some multi-formation tracking for the network robotic system. So the lecture today, so the main focus is on some new technology we have basically for control of the multi-agent and based on some development on the event-based control with some advanced control techniques. So, but if you need more information, you can contact me because each part there are some requirements for you to follow the material. But I have already mentioned the reference. But later on, if you find any difficulties to follow the material, you can contact me. So the first introduction. So introduction, we know about the network control is the history of the control come from the analog control to the centralized digital control system as we discussed before in the context of the network control. We have a topic of the decentralized control. This was the starting point. And then the decentralized control, we notice that there are some basic advantages in the handling the basic the system, but there could be some issues from the network side. And therefore, the distributed control system DCS was introduced as a potential application to the manufacturing process control. So because in the DCS, you have two parts. One, you have a networks for communication and the monitoring. And then you can see that how to look at the network complexity is some challenge we have in the distributed control. So the feed bus control system FCS was introduced after DCS and then the ICCS is an integration of the control and communication 1988, and then the network control in 1998, and then coming to the CPS. As we are talking about the CPS, it means the control, actuators, sensors, basically are integrated with some digital blocks evolving according to discrete events as a cyber. So it means that this integration of the basic this component, it can basically can introduce the CP. So these are the development of the control systems. So that's it. We are talking about the network. We talked about the network control as a distributed, as a complete distributed. So as you see in this case, we talked also in the previous lectures. So you can use this structure also for the estimators. But there is some integration of the sensor, controllers, and also actuators. But you should think about different configurations. So you see that the data will be sent over the networks. So you can also think about the distributed the filtering system. So it means that you have a target plan, you have a sensors, you have a filtering, and then you can get some error signals. So if you want to take it to the network-based filtering, so you need to take your sensor data over the network. So now you can see that in both cases, so in the case of the network control system or the network-based filtering, so there are some issues about the networks and there are a lot of complexity, and always in this course we talk about the complexity of the networks. Okay, so we noticed that in the network there are some issues about the time delay, packet disorder, packet dropout, quantization, And this could be they can provide some nonlinear physical plan. So if the network will be considered, the system is a totally nonlinear, and then there could be some challenge with classical control theory. So that's it, it's difficult to design the control. So you need to learn how to deal with this complexity in the control theory and how to design the suitable control methods to deal with this problem. Okay, so another topic I want to introduce from the CPS for the larger scale could be some context of the multi-agent system. So multi-agent system are the system that consists of the multiple agent, so with several sensor actuators and the capability to communicate with each other. So now you can see that in the context of the multi-agent, so you need to look at the the data from the sensors, how the actuators can react to the sensor, to the controller, and all the communication between the agent is through the networks. So there are some applications. So basically, the several applications for the multi-agent, like the automated highway, emergency patient transportation, so air traffic control, satellite formation, robotic formation, flight formation. So now you see that you could expect so many applications for the multi-agent system. So one application could be also interesting to discuss is about the multi-agent system intelligent manufacturing. So there is the cyber physical system. So architecture integrates the production and quality control in the multi-state production line. So this is a production line. You see there a lot of station number n plus one. So all these stations, there's some integration of the CPS in terms of some machines and some operation to produce some material. So now you can see that this is the one layers. So if you want to look at the implementation of the multi-agent, so you can consider to add additional layers. So these are the some basic distributed of the agent and the different layers in the hierarchical form, and they can also communicate through this cloud, okay? So this is a cloud-based control. So, but the purpose is to improve the quality, this production line. So therefore, in this quality, so there is in the context of the intelligent manufacturing, there is a keyword of the ZDM, is the zero defect manufacturing. If you want to reach the zero defect manufacturing, so based on this distributed and decentralized approach based on the multi-agent system, so you need to learn how to look at the communication, how to look at the controlling of this hierarchical multi-agent system. So now you see that there is a lot of difficulties. So in the context of CPS, and then if you want to design the suitable control, so you need to look at some advanced techniques in the control theory, and that's it for today. I want to tell you some advanced concept to look at the control strategies. So they're based on some features from the networks, some event-based. It means that we should be discussed in this context. So the traditional control is a point-to-point control. You see the data from the sensor go to the controller. It's a classical control. But if you come to the distributed control, you can see that the P1 to Pn is a distributed plans, and then all the measured data Y1 up to Yn can be sent to the communication networks to the different controllers. But please pay attention that the input to each controller, for example, C1, is the measurement Y1 and also some neighbor data. So here the Yj belong to the set N1T. What does it mean N1T? The N1T is the neighbor plans, neighbor system to the system number one. and from the neighbor system, so there is some additional information. So it means that you don't need to get all the information for the sensor, for the basic, for the control one. Only you need to look at some information from the neighbor system. But this could be sort of a distributed system over the networks. So another topic we have in the multi-agents and multi-agent formation. It means that you have a group of the agent with some specific task. So if the agent has a specific task, they can do some formation. For example, for this system, so if you have this multi-agent systems, if they go to the formation stabilization, they can come to this shape, okay? It's a triangular shape, and this is a multi-agent formation. So in the multi-agent formation, you need to look at the position and of each agent. So for the agent number I, so you can see that you have a position pi, you can get the velocity. So in this case, you can also design you can think about how to control basically this position. And therefore the control of this is a very simple dynamics. So for each agent, you can maybe you can think about this simple dynamics, how to design the control signal UI to get one particular position for agent number I. So these are some textbooks if you want to look at some fundamental aspect of the formation control. So formation control, it can be also used in the robotics, basically the self-assembly. You see that how to reach from the centralized control to the decentralized control. And basically in the history, you can see that how the manufacturing system or the industrial or the assembly machines has been developed. So you can see that from traditional robot assembly in the centralized control to the programmable vector field. And if you come to self-assembly, then the formation control. So now the formation control, you are very close to the decentralized control, and that's it, the multi-agent formation control. So basically, we are talking about the fully decentralized control, but only the point is that in this context, there are many complexities based on the security of the data, based on the network data. So, and also in terms of the control, because the system should do some tasks. So another project we did also in the past about the structural vibration control. I give you some additional information to see that how this can be worked in the context of the multi-agent. So maybe also it is also useful in India. Maybe there are many earthquakes in the north of the India. So the building should be protected. If you want to protect the building against the earthquake, so you can add some actuation device. You can see. So these actuation are distributed actuators. And then if you want to control, it's difficult because you need to give some data. So for the control design. But how to look at the control design? For example, you can partition the whole system to the many subsystems from subsystem 1 to the subsystem R, and each subsystem has some neighbor systems, or we call it the floor or story. So if you want to control the subsystem R, so for example, you have the information YR, maybe the position of the floor, number R, but there could be some other information for other subsystems. But the point is that for controlling the subsystem R, so you can design some advanced control. For example, you can take the YR data to this control agent, and control agent, you can basically design the control for this subsystem R. So maybe you can follow some idea from multi-agent for such as the replicator dynamics. It means that you can design some control based on the local information and also based on the neighbor information. And this is the task in the multi-agent. You need to look at your data. Okay, so the control of the multi-agent from the theoretical point of view, so you have a many subsystems. So some individual subsystem, they can only access the information of their neighbor because of the communication constraint. So you have some limitation over the data from the neighbor system. And therefore, the system has to be controlled by a distributed control protocol. So we call it the nearest neighbor rule. Okay, so these neighbor information, so the can be taken to the account, and all the agent in the group, they should have a common objective. So in the multi-agent, all the agents have a common objective. So they leading to the collective behaviors, and the global behavior of the system is jointly dictated by the system dynamics and the communication topology. So now you see that the total behavior of the multi-agent system depends on the network and also depends on the dynamic of the agents. So the basic control problem for the multi-agent is a consensus. Consensus is a basic problem, and maybe I'll talk more about this today. So for the consensus problem, so you could realize it based on the leaderless consensus problem. It means that there is no leader, there is no any external information, and then the output of all the agent of the multi-agent system asymptotically approach a common trajectory via distributed control law. Okay, there is no external information, and the information of each agent, the output of each agent, should asymptotically approach a common trajectories based on the control design. There is another consensus problem. It's a leader following consensus problem. For this leader following consensus problem, there is a leader information, and other followers, they should follow the information given by the leader. And that's it. You need to design the control such that all the followers, the output of all the followers, they can follow exactly the information given by the leader. Of course, there is some other variation of the consensus problem. For example, you can look at the synchronization, flocking, swarming. So there is some other kind of the development. So this is one of the results. If you are interested to all the mathematical or the research, you can look at this publication given in the bottom part. So if you look at this publication, you can see more details. The first thing I want to talk about is distributed agent control for the multi-agent systems. So this is basically the multi-agent system. We call it a heterogeneous agent. Heterogeneous agent, so basically says that each agent has a different dynamics, AI. So if we call it a heterogeneous agent, means that all the agent in the equation number 2, for example, agent I, it has a matrix AI. If the AI are different for different agent, we call it a heterogeneous agent. But if the AI are the same for all the agents, this is non-heterogeneous. So these are the two different keywords. So here the UI is the control signal for the agent number I. Omega IT is the disturbance for the agent number I. And we assume that this agent is a controllable, AI, BI is a stabilizable. Do you remember yesterday? Yesterday I talked about a stabilizable. Do you remember? This is a very important topic. AI, BI is stabilizable, and AI CI is detectable. So these two topics I explained you yesterday. These are different from controllable and also observable. Here we call it stabilizable and detectable. So these are the important concepts in control. So we can define the leader dynamics from equation number 3. If we look at the leader dynamics, you can see that there is one state variable T psi O. There is some metric S and R. These two matrices, so they can define the information profile of the output of the leader agent. So the YO is the output of the leader agent, and then this output depends to these two matrices, okay? So here also the real part of we have also some assumption. So basically we have also some assumption on the metric S and R you can see here. Okay, so now based on this information of the leader and also the dynamics of the followers, we need to follow what is the consensus problem. So another assumption is about the communication protocol or the graph for this case. So we assume that all the agent we have, it contains a spanning tree with the leader as its roots. It means that if you look at this distribution of the agent, this is the one graph. So in this graph, if we call it there is a spanning trees, it means that there is the one root from the leader to all the agents. For example, here there is a spanning tree because information from the leader, it can reach to other agent, you see. And this means that we have access to this leader, they have access to all the agents. So this is the one assumption that we say that there is a spanning tree with the leader as its roots, and this is the meaning of the spanning tree. So another assumption is that all the agents are time synchronized with the sampling period at each time instance. So now this is important that the agent or the time is synchronized. So it means that there is no any asynchronous basically in the data transmission over the networks. So another assumption, so based on this assumption number 4, assumption number 5, it says that you can let the sampling time tau k, this sampling time, the difference between the two time instance, so tk plus 1 the tk. So, and then here you have a sampling period tau k. So this sampling period takes the values from the set the t1 to tn. And the tj are the sum allowable sampling period. So this assumption number 5, it says that so all the agent, they can take they can take the next sampling time because you need to know what is the next sampling time or the next time instant. So the next time instant for each agent depends on the tau k, and the tau k is one of the values from the t1 to tn, and this tj is we call it as the sampling periods. And each agent has a particular sampling period. And then by taking based on this T1 to Tn, so the agent can decide what is the next time instant. And therefore, if you want to control the multi-agent, you need to control what is the next tk plus 1. And this is basically what we are expecting in the controlling of the multi-agent. But this assumption is also important to say that what is the allowable, what is how much TI, so it could be basically the allowed for each agent to be taken, and they should take it from the set number of the metric, the set 5. So let's back to the followers, to the agents. So the agents, so they can be representing the discrete time like this, based on the same assumption that we can discretize it for each sampling time. And if you look at this discretization, so the equation number 4, discretization for the leader agent, you can obtain all the matrices that you can see in the equation number 4 from this mathematical model. So now you have a discrete time model of the heterogeneous agent. And then you can also think about this switch discrete time model. So now the switch discrete time model, it says that in this equation number 6, so you can add the vector rho k, the parameter rho k. So this gives you some switching because if you look at here, so the agent, can switch from one status to another status, and there could be different realization or the different possible realization for these matrices you can obtain it. So the meaning of the row K, because row K, if you want to know what does it mean, the switching signal row K. So the switching signal row K is a switching time sequence is defined at a different time from KO, K1 to KL, and also the handling time between the two sampling, the two time instant, KL and K plus 1. And this is the dual time of the basic the S engage subsystem. It means that because in previous slide, when you discretize the leader, the followers, so you could expect a different basic the subsystem. And then if you want to engage, so particular subsystem row K vector S, it means that you can engage the particular subsystem to the model. So now the row K, it can be introduced as a sort of a switching signal, and this belongs to these particular sets from 1 to n. So in this case, so we can basically to define the switching signal, and this model now it can be introduced as a switch a discrete time model. Okay, so for this switch discrete time model with the parameter row K, so then you can define this, design this control. The control protocol number 8, so it can be designed based on this mathematical formulation, but please pay attention that here there could be some matrices, so they should follow some assumption like this. So I think if you are familiar with the multi-agent, so you can see that the sigma ij, so they can also depend to the parameter aij as a Laplacian parameter of the multi-agent. And also there could be some information from the neighbors of the agent number I. So here there could be some information for basically the T psi ij. So because here we have some dynamics for the T psi I. So it means that for agent number I, you can design this dynamical control. So because UIK can be designed, if you could find some matrices like the matrix Ki rho K, this matrix Ki rho K is a control gain matrix. So you can, or you should be also able to obtain it. But what about the other terms? So these are the some issues, some information coming from the major agent or the local agent. But this protocol was introduced, and another information I should explain from this control protocol is also about this GI. The parameter GI you can see is appear here is important as a pinning gain of protocol I. So the pinning gain means that the T psi O, the O means the leader part. Information of the leader can be directly comes to the agent number I. You see the leader can have access to the agent because the GI is positive. If the GI becomes zeros, it means that the leader cannot send information to the agent number I. So now we can see that if the GI is positive, it says that the follower number I, they can access to the information of the leader. But if the GI becomes zeros, it means the followers cannot receive information of the leader. So in these scenarios, the matrix K, the matrix H, so K and H are the control gains you need to obtain. So now the control gain is the matrix K, matrix H, and should be calculated. Okay, so other parameters are the some design parameters, and basically you don't need to calculate it, just Ki and also the H rho K. Okay, so the other parameter like the matrix pi I and also the matrix the gamma I rho K. So these are the assumed distribution to the following regulation equation. So here we have some algebraic equation, and these two matrices. So the red I have represented with the red light. So they can be obtained from by solving this regulation equation. You can obtain the pi I and the rho I, gamma I, rho k. And also for solving the control problem, so we should also assume that this rank of this metric should be such this way. So in order to be able to solve this equation, if you want to solve equation number 10, so this rank condition so should be satisfied. Okay, so now the problem is this: how to find K, how to find H, and that's it. I'm trying to explain it in more details. So the problem is that design the output feedback control. It means that for design the output feedback control, because here you have information via K for the sensor for the agent number I, and therefore you need to design the output feedback control. So the output feedback control says that if the K goes to infinity, the error vector, the error should go to 0. The norm of the error should go to zeros. And then if there is a omega, the disturbance is zeros. If the disturbance is not zeros, so basically you can look at some initial conditions like this, and then the H infinity condition should be satisfied. It means that the energy of the disturbance over the energy of the error signal should be bounded to the gamma. And this is the one H infinity condition we have basically for solving this problem. So in this output feedback control, you need to remember that there are some signals like the error signal EIK is a difference between the output of the agent I and also the leader, and also the T psi IK can be calculated from this mathematical formulation. And of course, based on this representation, you can find equation 11. Okay, but equation 11 is still a matrix K, and so the gain K and the gain H. So you don't have it, you need to design it. And this is the reason that we need to look at some theorem. So in the theorem number 1, it says that this problem can be solved. So if the following the n system, because if you consider this n system for each agent number I, so this should be simultaneously exponentially stable if the disturbance is zeros, and if the disturbance is not zeros, they should satisfy the H infinity performance level, the gamma I for agent number I, and also the following n system, and this n system you can see in equation number 13, it should be simultaneously exponentially stable. And okay, so now you can see that if this equation number 12, if they want to satisfy basically the H infinity condition gamma I, so this system also there should be asymptotically stable, and this is means that you need to find the gain H basically to design to satisfy this asymptotic stability of the system. And in this case, you need to remember that in the matrix 18, the I, the control gain is also appeared the matrix Ki, the gain Ki. So now in total, you can see that the H and the K are appeared in equation 13, equation 12, and now the task is how to calculate these two parameters. Okay, so we have proposed some theorems, but this theorem, for example, it says that if you, for this prescribed H infinity level gamma I, so and then if you solve this linear matrix inequality like number 14, and also with some sort of the condition equation 15, and also some condition over the sampling period TA bigger than this. So if these conditions are satisfied, basically you can satisfy the asymptotical stability of the both systems. So it means that the both condition can be satisfied. But of course, more details you can find in the reference I gave you in the advance. But I just show you the main idea. So in this theorem, you remember that we introduced the switching signal rho tau. So this switching signal, so here we assume that for the time between the two time instant ko and k, so we assume that the n row is the number of the switching of the row tau over this time period. And if the n row, the number of the switch, the n row, the number of the switching of the signal is less than this, and we assume that this condition is satisfied, and this is we call it the average dual time, so ADT. So if you want to know that what is the ADT, in the ADT, the average dual time in the switching signal, so we assume that there is a parameter TA, and then the number of the switching in the time period between the KO and K, so the number of the switching should be less than this. So in this theorem, we also satisfy this ADT, the average dual time, and based on this parameter n row, and then if we look at, for example, this case, so this condition also TA. So this TA, in a condition number 16, it says that this TA should be bigger than this, and therefore we have the same idea about the average dual time based on the number of the switching. Okay, so we also propose another theorem. So basically, for solving this problem, it says that if we want to design the control, so if the average dual time, the TA, bigger than this, and if there is some this condition are satisfied for each agent number I, and then you can calculate the gains of this basically the controller, the output feedback control from these two mathematical formulation. In these two mathematical formulation, you can solve the problem of the output feedback control by designing or by finding these unknown matrices from LMI. So you need to solve LMI. By solving this LMI, you can find L, U, and other parameters, then we can calculate these two gains. Okay, so about the simulation, I show you a very simple simulation. Assume that there is a leader O, there are 5 agents, and then here there is a followers, they use the sample data of the position information for control design. So each agent can be modeled with the double integrator dynamics with a different type of actuator models. So this is a model of each agent. So each agent has a different parameter A, C, D, and these are the made for vector B, and this is basically the dynamic or the kinematics or the dynamics of each agent 1 to 5. And then there is a two matrix S and R. They can also represent the leader dynamics, and this is modeling, okay? So now you have a model for agent I, 1 to 5, and also the agent O for the leader part. So here these are the sum for simulation. We choose the different parameter A to EI. So basically for each agent from 1 to 5. So here we are taking the sampling process as a non-uniform, and the sampling period is taken from the set file. You remember that the sampling period was important because the next time instant of the agent is taken based on this parameter 0.1, 0.2 seconds, because based on these parameters, so you can see that the sampling period is non-uniform. You see, agent number 1, agent can take the different sampling time, and therefore this process is a non-uniform. Okay, so by solving this equation 8, you can find some solution to that the algebraic equation, gamma I and also the pi is. For agent 1 to 5, you can calculate all the information from equation 8. Okay, so there are some parameters for solving the theorem. So like for average real time and other parameters. So you can set some values and then start to do the simulation. So when you solve the LMI toolbox in MATLAB, so the MATLAB gives you these control gains. You see K11 to K52. It means all the agents basically the gains. You can for the output feedback control you can obtain it with the two matrices H1 H2. So you can obtain from the toolbox LMI in MATLAB. So this picture shows the trajectory of the position. When there is no disturbance, then you can see that all the agent, you see, the red the dashed line is the YO, is the leader information, and the other are the agent information. So you see all the agent, they can follow the leader information, and this means a consensus problem, the tracking. And this is the error tracking, you see? And after the maybe 8 second or 10 second, all the agent they can reach the error can approach to zero, and this means that the tracking can be satisfied. So if there is some disturbance, so like this sign function for each agent, there could be some deviation in the error signal, but again, it's a zero. It means it's a robust. So again, these are some tracking of the sign function. But if you give the sign function, so the performance is like this. But in fact, the position error can be regulated or can be attenuated. The disturbance effect can be attenuated. Okay, so these are some values for the H infinity conditions. Level of the gamma, so the performance can be obtained like this. Okay, so in the first part, I introduced the output feedback consensus control for the class of the heterogeneous agent in the presence of the disturbance and the non-uniform sampling process. So we look at some output tracking problem based on the discrete time switch system, and then this theory is based on the Lyapunov of base theory. So you can guarantee that you can find some sufficient condition for stability. So of course, this is the output feedback problem, and then you know that the output feedback problem is a non-convex optimization problem. But here in this publication, so we try to solve it based on the LMIs, and that's it. This result is important. Okay, so the next part, I'm going to talk about the effect of the networks, about the event-based, and also to show you that how you can design some advanced control, so such as the distributed MPC, the model predictive control. But tomorrow I will talk about MPC, but today also I try to introduce you to MPC, but in more details, we can also some basics you can see tomorrow. But this result you can find from this publication. If you go to the publication number 4, so you can find the source of this presentation, this article. So here we have a group of M agents. So here we can see that again we have an agent AI is a heterogeneous agent. So it's a linear and with the dynamic XI and also the control signal UI. So here we assume that the AI and BI is a controllable or stabilizable. And also we assume that for agent number I, so it can receive information from at least one agent J. So without communication delay, it means that we assume that agent I can receive information from the another agent or major agent, so without any delay. Okay. So for each agent I, so we assume that the cost function solved at any triggering time instant TIR. So now I want to introduce one topic as a self-triggering the BMPC. Is what the distributed model predictive control. It means that if the agent I, so basically receive they should minimize the one cost function. So at any time instant TIR. So you can define the cost function like 22. So this cost function is a quadratic cost function. It has two parts. One part is a network effect because this is the cost of the networks. And by changing the gamma I, so you can control the cost of the networks. And there is another cost function, JIC. So JIC is for the performance cost function. And therefore, so we can define this total cost function JI based on JIC from this mathematical model. So here you can see that the TI is the difference between the two sampling two time instant, and this is the triggering time. It means that the TIR is the current time instant, but when is the next triggering time is a TIR plus one. So the question is here that how to find this, because if you want to find this, you need to know what is your TI, the time period, and then you need to remember that the TI is appeared here in the network cost, and therefore this network cost should be also minimized. Okay, so now this is the problem. This is the cost function for the agent I. And here we have also proposed one algorithm for solving this problem. So in this problem, we can see that we can look at the local state measurement. So it means that agent I, it has a local measurement. And then the agent I can receive some information from the neighbor agent J. So at this time instant TJCI. Another point is that the control signal UJ star is the control signal is given also applied to the agent J. So these two information, so we descend to the agent number I. And agent number I should look at the receiving information from agent J based on the state information and also control signal information. And then the agent I should solve one problem PI in the online at the triggering instant TIR in order to find the next triggering time R plus one and also the control signal. So the optimization problem in the MPC in the model predictive control is this. So we need to minimize the cost function JI, includes the state information for agent I at the time instant TIR, control signal for agent I at the time instant TIR, and also the time interval, the TI. Because the TI is, as I told you before, that in this case, is important to find the next time instant TIR plus one. Okay, if you minimize the cost respect to the time interval TI and the control action UI, so there could be some constraint. This constraint is the prediction because based on the prediction of the next values of the state I at this horizon L, if you have a horizon L, you can make a prediction of the state information with the horizon L based on this mathematical model. And also you can also do a local estimation of the other state estimation of the state of other neighbor agent. So this is very interesting that in these control scenarios, so agent I, they can do prediction for itself, and also the agent I, they can start to do the estimation of the predict estimation of the other state neighbor J in the one horizon L. And this is also very interesting that the agent I, they can also try to update information of the other agent. So in total, there is also the time the parameter Ti. So the parameter Ti in this mathematical model, so it belongs to one specific interval, to a specific set. So, and then the agent I can take the different values of the Ti from this set, and this is the maximum upper bound of the time interval. Because this MPC is computational is expensive, so you can add some constraint over the control signal and says that the control signal can be updated in the state form. You see, there is some updated over the control signal in the different time interval in the state form, just to minimize basically just to minimize the computation time. So we propose one algorithm as a self-triggering the DMPC. So in this case, there is offline calculation. There is an online processing time in the real time. But the offline, you need to set some initial parameters, basically, but for solving this condition of this research. And then there is some sort of the online calculation. It says that for agent I, so agent I, they should do some estimation of the other neighbor agent in the horizon L, and agent based on this estimation part, and then agent I should solve this problem P tilde I. So this problem has been introduced just to obtain the Ti star. What is the values of the time interval for agent I? And this should be defined from the minimization of this cost function over the Ti. Okay, so if you solve this kind of the online processing, so you can obtain the control signal from this mathematical form. So control signal has a two information, like the gain FII for the local information, and other gain, control gain, respect to the information of a state of a neighbor agent. So because agent J belongs to NR. So very briefly, for you, important information is that if you follow this self-triggering DMPC, so basically you can obtain two information. One information is what is the next control signal, and what is the next, basically the time instant TIR plus one. So these two information, so basically can be used for the self-triggering DMPC. Of course, there are some remarks, but maybe we can skip it. But this is just to say that how the control signal can be constructed. And control signal is given for one time frame between the two time instant, and then the next time instant after the next interval, the control signal can be updated. So we also propose one theory for stability. It says that the stability of the whole system can be guaranteed based on this condition. And of course, this can be also proven. So something for your information that stability is the Lyapunov base. It means that by choosing this quadratic Lyapunov function, so basically you can guarantee the stability. But this means that the agent asynchronously and the aperiodically update the control input and broadcast the current information. So this means that the Lyapunov base has been approach has been used for the stability proof. So for simulation, you can choose maybe the one leader and also the four basically the four the robots with this information. So the robot basically we look at this manipulator, and it has some DC motor for actuation, and you have a rigid thing. So there is a rotation angle QI, and this mathematical model can be written for this actuation part. But if you notice that this model of this manipulator is nonlinear, but if you start to linearize, and then you can find a linear multi-agent. So now for this, after the linearization with this sampling time, so you can find some linear equation. So for this multi-agent. So now you can think about like this. For controlling this multi-agent, so you could say that I can take some neighbor sets for this for manipulator. For example, so you can say that if, for agent number 1, so the neighbor agent is number 4. For agent number 2, the neighbor is agent 1. For agent number 3, the neighbor is agent number 2, and for agent number 4, the neighbor is agent 3. What does it mean? It means that each agent can receive the data from the neighbor agent. Okay, so now you need to solve this algorithm for this self-triggering DMPC. So by solving this, the problem PI, so you can calculate this information from from the algorithm. So if we look at the result, you can see that basically the result here, there are four basic plots. So the TT is the time triggering, the DMPC, and also ST is a self-triggering DMPC. So now you can see that the ST DMPC, the dot line, they can also follow the result of the TT DMPC for the 4 agents. These are the angle of the agent 1 to 4. But maybe you want to know what is the benefits of the ST DMPC, but I can show you later. So these are the control signals for the agent 1 to 4. Then you can see that all the control signal can be updated at a different time interval. And this control signal basically is based on the self-triggering DMPC. So these are the triggering instance of the 4 robot manipulator under the STDMPC. So from the agent 1 to 4, then you can see that at which time, so the basic at which time instant the control can be updated. So that's it. So based on the STDMPC, you don't need to trigger the agent at any time. There is some particular time you can obtain from the optimization of the MPC. Okay, so the next slide is about the cost function. So in this slide, you can see that STDMPC and compared to the other time triggering DMPC, so the result, it gives you these values, but this is about the control performance, JC. But if you want to know that what is the advantage of STDMPC, you can come to this slide. In this slide, you can see that the total cost J, so for the STDMPC is much less than the others, and the total cost can be minimized if you are using the STDMPC. But if you look at the other traditional DMPC based on the time triggering, so you see that the total cost is higher than this. And this means that this approach is more effective in terms of the basically implementation over the networks. So this slide shows the relation between the control performance JC and also the number of communication, and also the gamma is the communication for the parameter for the network cost. Okay, so but if you look at it, if the gamma is a small values, then you can see that the number of communication increase, and this is your control performance JC. But if the gamma increase, then you have a less basic communication, number of communication, and also the control performance increase. So now if you want to minimize, so you need to find the optimal value for the gamma, and therefore this could be very interesting research, how to consider how to find this optimal value for the gamma This could be another challenge, but in this research, the gamma is fixed, but this could be another interesting question, how to find maybe the optimal value for the gamma. So here I try to introduce the self-triggering the DMPC for the unconstrained linear multi-agent system. So we notice that the DMPC, so based on the triggering instant and control inputs are jointly optimized by minimizing the cost function involving the communication cost and the control performance cost. So we could provide the sufficient condition. So basically on the design parameter to ensure the system, basically the stability, and also demonstrate the effectiveness of the proposed self-triggered DMPC method on cooperation control of the flow robot manipulator. So if there is a time, I want to also show you something about the multi-formation tracking of the network heterogeneous robotic system. So here you can also follow basically this presentation from this reference. So if you heterogeneous robotic system, we have an end robot. And the robot, we have also some assumption on the graph. Basically, so it means that this robot follow this particular graph. This graph has is a directed graph with several parameters. So one is the set V is the vertex set in the graph theory, and also the T psi is the edge set. And also the set A is the Laplacian or the weighted adjacent metric of basically for the graph. So usually in the graph theory, so we have some information like this. So the vertex set and edge set and also the adjacent metrics. So the another information for you is that the age of EIJ. So basically, so in the set implies that the robot I can directly receive information from the robot J. Okay. So another thing that AIJ in the adjacent matrix is positive if the robot I cooperates with the robot J. And if the AIJ is negative, it means that the robot I includes some competition with the robot J. Okay, so if it's positive or negative means the cooperation or competition. If the AIJ is zero, it means there is no connection between agent I and agent J. So here we assume that there are no self loops if the AII is zeros. If the AII becomes zeros, it means that there are no self loops. And then another information is that the Laplacian metrics in the multi-agent, so based on Lij, they can also satisfy this formulation between the Laplacian matrix Lii and also this adjacent parameter Aij. So they can also satisfy this formulation. So now, if you work on the multi-agent system, so in the context of the CPS, so you need to remember that there are some fundamental formulation from the graph theory, and then you need to follow this foundation. Okay, so another point, as we discussed before, Ni denote the neighbor set of the robot I. So here in this research, we try to do some decomposition of all the agent to M stop networks. It means that you can introduce the sub networks, for example, the sub network L with the VL epsilon and AL. It means that you have M groups or you have M sub networks. And then this subnetwork, there is no overlap in the node, and therefore there is some assumption on the subnetworks. And then you can also look at this point that the total vertexes VL, So the can be calculated based on this information you can see here is utilized to label the robot in the L subnetworks. So another thing is that the whole partitioning of the V1 to Vn. So there is an acyclic partitioning of the graph G. Basically, if there are no cycle in the interaction of the subnetworks. So maybe another interesting thing for you about the pinning metrics. The matrix P is the pinning matrix. What does it mean? It means that what is the interaction between the robot and also in each subnetworks and also the virtual leader assigned to each subnetworks. So if the BI is positive, it means that the robot I can receive directly information from the virtual leader. And if the BI is zeros, it means that the robot I cannot receive information from the virtual leader. So in this case, the pinning matrix with respect to the graph GL, so you can define it as a BL, and also the sequence of all the partitioning of the set V1 to Vn. So it's an acyclic partition of the directed graph G. Okay, so this is a graph theory, and graph theory is a fundamental issue in the mathematics, but we try to put I introduce it to you. But if you are not familiar with the graph theory, but if you're interested in the multi-agent, so you can start to study some basics about the graph theory, and then you can understand all the mathematics in this presentation. So basically, the final result is a Laplacian matrix. So this Laplacian matrix has such a partitioning. It says that each Li is represented Laplacian for each subnetwork L. And Lij is basically the interaction between the group GL and the group L. So this interaction between them. So in this network heterogeneous robotic system, so we try to introduce the dynamics and also kinematics of this net NHRS. So here this is a nonlinear function, and then based on the inertia, centrifugal forces and gravitational forces, and also the disturbance Di, and also we have a torque tau I. And these xi and the velocity are the kinematics. So of course, here there are some uncertainty in the inertia, centrifugal force, and gravitational. And then you can, there are some uncertainty like the delta mi, delta ci, delta gi. But if you put it together, you can find equation 34. So equation 34, so basically, it consists of the nominal values, basically for all the parameter of the robot. And also on the right side, you have an actuator. It means that you have a control signal tau I. And the FIT is the disturbance is also added here. Okay, so here we assume that this disturbance or this uncertainty is satisfied this condition. So something about the virtual leader. So in this research, we try to introduce so basically virtual leader for each subnetworks. It means the subnetworks L, it has a virtual leader. It gives the virtual velocity, virtual acceleration. So basically for each agent in the subnetwork L. Okay, so these are some information, and also all the agents in that subnetwork, they should follow this information. So here we assume that this acceleration is also bounded, and this is a basic one assumption we have on this dynamics. So the problem formulation that here we want to satisfy all the finite time, practical finite time, output multi-formation tracking, OMFT. it means that you need to look at the error signal for the position of agent I respect to the virtual leader for group number L. And then you have also some offset HI. It means that this error signal should approach to zeros, and it means that you can do the tracking. At the same time, the velocity of each agent I in the group number L, VI minus the virtual velocity for agent for the leader basically L. So this also should be regulated. Okay, so now you can see that for OMFD in a finite time, so this norm of the error signal should be bounded, and also the norm of the velocity of the error signal should be also bounded. And therefore, this is a condition basically we need to satisfy, basically for this particular case. Okay. So this slide shows the general framework of the proposed basic FDXC, the finite time hierarchical control algorithm. So this presentation is like this. So for agent number I, so if you want to design the control, so you need to do some estimation of the other state agent. So here we have used on the top one a distributed estimation layer. So this distributed estimation layer is based on the sliding mode control. Okay, so based on the sliding mode observer. So this sliding mode observer is a nonlinear sliding mode observer. And in this sliding mode observer, you can see that we have used information of the leader, virtual leader, for doing the estimation of the local agent I. And this information of estimation of the agent I, the position velocity, is taken to the control. So the control is based on the sliding mode control. By design, we want a sliding surface, an error signal, a sliding surface, and then here we have designed another sliding mode control. And this sliding mode control, they can give us basically the input signal tau I. So now you can see that the control signal here we have designed is based on the sliding mode observer and a sliding mode control. Okay, so in terms of the observer design or estimator based on this sliding mode estimator, so here we have a proof that this estimation error, so the error can converge to zeros and also in a finite time. So this has been guaranteed, but I'm not going to show you the proof, but if you are interested, you can look at the publication. And also, we also look at the finite time hierarchical control and how to design the control that I'll show you before. And we also noticed that the OMFD, this is the finite time output market formation tracking. It means that the error signal and the velocity of the error can be bounded. So this can be also proven. And these are the some information, but you need it in this theory, but I just show you that what mathematics we have. So let's look at one simulation result. In the simulation result for this network heterogeneous robotic system, so we have the 11 agent, and these 11 agents, they can be partitioned to the 3 groups. Group number 1, number 2, number 3. And then in this group, L1, L2, L3 are the virtual leaders. And then you can see that there are some parameters, either positive or negative, means either the collaboration or the competition between the agents. So the agent are there are 2 different models. Either the robot are the 2 degrees or the 3 degrees as a redundant robot. So then it says that here we have a 2 particular model of the robot. And for the 2 degrees robot, so we have this information for the mathematical model of the robot for the inertia and other parameters in the robot. And also we try to follow some estimated value for the corresponding to physical parameters for the robot we can obtain like this. And for the 3 degrees of the robot, for example, robot number 1, 4, 11, so we can also use this parameter for simulation part. And also the corresponding, the estimated value of this parameter of the robot we obtain like this. Okay, so these are the parameters of the model of the robot. And then we can see that the leader information, because there are 3 groups. For the group number 1, you can give this virtual leader information, position, velocity, acceleration. For the leader number 2, for the leader number 3. Okay, now you have a leader information. You have also the partitioning of the agent to the 3 groups. And then you can start to design the finite time hierarchical control based on a sliding mode control. So here you need to put some initial values, and also you can think about some external disturbance. And then you can also add some offset H1 to H11 as offset basically for the positioning, the formation tracking. So in this case, if we look at this picture, these are the pictures for the evolution of the xi, the position of agent I minus the offset hi. For the agent 1 and also the other agent to agent 11, you see all the plots for the position because this is in the xy coordinate. So in the Cartesian coordinate, so for the first xi1 and also xi2, so all they can be for. You see that all the difference is also bounded, and therefore even for the position and also estimation, so there is some sort of fluctuation, and it means that it shows that the values of the agent and also estimated values are bounded. So let's look at this slide. This slide is an error signal because the agent should follow the information of the virtual leaders. So now you can see that the error signal in the first coordinate and the second coordinate for all the agents from 1 to 11. So all you see are bounded. It means they are regulated to zeros, even if there are some fluctuation here and or here, these are also bounded, and it means that you can prove the boundedness of the formation tracking. And even if we look at the estimation of the error, again, you have the same result. It means that the tracking can be satisfied, and also always the error is bounded. So this slide shows about the evolution of the velocity state. Okay, for the coordinate 1 and 2, then you can see that the velocity is also regulated, and also fluctuation is bounded for all the agents. And if we look at this slide, this is about the velocity tracking errors. It means that the tracking errors, velocity tracking errors, E dot, is also bounded and also is regulated. And this means that the control signal, it works. So about the control signal, for example, for the robot 11, you can see that this is the control signal can be applied in the 3 axis, 1, 2, 3, because robot 11 is a 3-degree freedom robot, is a 3 dot. And then you can apply the 3 control signal like this. And all the control signals, they have such a fluctuation, but are also bounded. And then based on this control signal 11 for the robot 11, then you can see that the formation tracking for based on all these control signal. So formation tracking for all the agent 1 to 11, and also with having the 3 virtual leader L1, L2, L3. So they can follow these 3 shapes. So what does it mean? It means that each group of the agent 1, 2, 3, they can follow the information of the virtual leader, and they can complete a specific shape. You can see. Okay, but if you want to see specifically each part, I can show you here. So this is about the agent 1, 2, 3. And then you can see that this information of the agent based on the leader information, the green line, and after a starting time, 2.5, 4 seconds, 5 seconds, 10 seconds, you can see after some evolution, they can come to this triangular shape. And then it means that this is the formation and the robot got such a shape. So even for this particular case, for the agent 4 to 7, they can also follow the information of the leader number 2. And then you can see that after the taking the time, then they come to this square shape. You see this square shape, and then it means that the formation tracking has been satisfied. So this is for the agent 8, 9, 10, 11. And then you can see that they can follow the leader information number 3. And then you can see that after evolution at the time, so they can come to this particular shape. Okay, and this is basically we call it the formation tracking. So this is about the robot control. So if you have a control, if you don't have a control, and if you have a control, then what happened in the joint space? So now this is the result of the angle of the robot in the joint space. But previous result was in the task space. But if you use the kinematics of the robot come from the task space or the work space to the joint space, you can see that for the joint 11 Q11, so these are the angles, and then you can see that the robot has a very smooth angle. But if no control, you can see this picture on the top. Okay, so in this part of the research, I try to introduce the output formation tracking. So it's an important part for the network heterogeneous robotic system. You can design the control in the task space, even if there are some uncertainties, a disturbance, and also based on this shape of the directed graph. So here we can design some advanced control based on the sliding mode control, a sliding mode observer. And then you notice that based on the Lyapunov-based techniques, so you can satisfy the formation tracking. Okay, so this was this part, but I can send you this PPT. So if you have any question, you can come ask me now, or maybe you can ask me later. Do you have any question, any comments?
Yeah, participants, if you have any queries, interact with sir. Participants, if you have any queries, you can ask. Is my voice audible, sir?
Yes, yes, probably, yes.
Sir, I just have a very small query on behalf of the participants. Uh, uh, Actually, in this course, we have covered the sliding mode control designs, and also you have given some preliminary ideas about the H infinity control. And in the state of the art works, both the control algorithms have been identified as a famous robust control theorems. So if I want to differentiate the merits of these two from the applications of cyber physical systems, then what are the possible attributes that we can consider for differentiating both the algorithms?
Yes, actually, you know that the cybersecurity from the control point of view, so you can take it as you can model it as some abrupt change in your sensor data. And that's it in the first part of my presentation when I talk about some measurement outliers. So it means that you have some maybe cyber attacks. So that's it in control. Because you know that we are talking about one cyber security for CPS. So now if you are as a control engineer, if you want to start to mathematicize your problem, so you need to remember that any kind of the cyber attacks, they can change the data. And the data comes from the sensor. And therefore, if you want to deal with the cyber security, you need to look at the resilience of your estimator, the resilience of your observer. And therefore, in the first part of my presentation, I try to tell you that how to deal with the some issues like the cyber attacks from the sensor and how to design the better estimator and better estimation. So this is a very important. Of course, if you want to teach the cybersecurity, you can talk about the different protocols, the different issues. But for us, in the control side, we need mathematics. So the easiest way or the one assumption you can consider to add all the attacks to your sensor data and then to discuss about the measurement. And therefore, measurement is the important part. So in my group, we are talking, we are designing different estimators. And you notice that today I presented a nonlinear estimator, and this is a basically very important part, and how to deal with the saturation come from the attacks. So the second part of the presentation, I came to the control of the CPS in terms of the modeling based on the multi-agent, because if you know the multi-agent, so in the group of the agent, they can do some sort of this, they can define some sort of a cyber physical system. And then there is a lot of issues about the network, the control, and I try to introduce you different control strategies. Output feedback control, multi-formation. Multi-formation control is a very hot topic. And also we discussed about some sort of the self-triggering NPC. But tomorrow I have prepared some slide about the fundamental of the NPC. And then tomorrow we have another lecture about NPC, and then we can discuss more details about NPC also tomorrow.
One more query I have, sir. You also have discussed the same during your presentations, that when we start the design of a controller, we always have a valid assumptions that the matrix pair A and B is controllables. So sometimes what we face from the reviewer sides, in the real-time practice, it is not possible to completely measure all the system variables. So if all the system variables are not measurable in the real-time situations, then considering the assumptions that the AB matrix pair is completely controllable, how can we justify this statement or these assumptions?
Okay, this is a good assumption. So yesterday I also talked about two concepts. One is that A and B is a controllable or a stabilizable. So usually the controllable is difficult to satisfy, and therefore you need to get down to the stabilizable. So that's it. This assumption in the control design, if you follow some strategies, so that if you want to do this based on the state feedback control, so you need to satisfy the A and B should be controllable. But if we don't have such a basic, if you cannot fulfill the stabilizability of A and B, so you cannot design the control based on a state feedback control. Then you need to move to the output feedback control. So it means that you need to change your control strategy. So basically, because what we say is that A and B is a controllable because you want to focus on the state feedback control. But if you focus on the output feedback control, then you don't need this assumption. Then you need to change your strategy.
Okay, sir. Thank you.
Okay, thank you.
If
I
there
will
are any other
send you.
queries, the participant can place their queries. The session is open. Any other query from the participants end?
Sir, I have a question.
Yes.
How zero
Please.
how zero defect manufacturing based on distributed and decentralized approach?
Yes, this is a good question because this is our one European project. I put this information. So because India, there is a lot of manufacturing companies. So if they want to come to the enhancing the quality of the control, the product, so the ZDM, zero defect manufacturing is very important topic. But the question is how to make it. So if you want to realize the ZDM, you need to divide your control operation to the different layers. One layer is the system layers. There is a lot of the equipment, like a robot, machines. The second layer is maybe some observer, some human layers, or go to the maybe the higher layers. Maybe there are some other sort of agent they can check the quality. So it means that, but sometimes these layers are the agent based on some monitoring. So you need to do some supervisory monitoring. But sometimes the layers or the agent can be introduced as a human. Maybe some sort of the human can monitor the quality. But in fact, in the ZDM context, on the top, we have a cloud. The cloud is all the data from all the machines goes to one cloud. And the cloud can be accessible by maybe the company manager or some human or expert. And then the expert can check the quality, and then they can give the set point to the system operation. So very briefly, in the context of the using the multi-agent for the ZDM, zero defect manufacturing, so the system should be able to find the set point for each operating point of the machines. So how to give the set point, you need to look at the knowledge, and this knowledge goes from the higher level of the multi-agent system. And then this knowledge, also the human can also give some additional knowledge as expert knowledge, and then this set point can be generated to give to each agent. So, but briefly, I think the last part of my presentation today, I talked about the multi-formation. You notice that I talk about a virtual leader. Sometimes in the zero defect manufacturing, you have some virtual, basically the virtual leader, they try to basically show you this information. So I think I have maybe one photo to show you that how it can be satisfied. So just a moment, I can try to find one picture. So okay, can you see my screen or?
Yes, sir, it is visible.
Okay. So in this slide, you can see that these are the different agents. So agent number 1, 2, 3, 4, but they have partitioned the two parts, part A, part B. And this is leader information. And they want to generate the surface and the robot, these are the robot, they can collaborate together. So if you want to reach the zero defect manufacturing, so the system should be able to give the right set point, because this leader, they can give some set point to basically to this group number 1. or to the group number 2. And therefore, so this kind of the information is given by the leader. And if the leader gives the good information, so it means that you are able to reach to the better quality. So in fact, the topic of the zero defect manufacturing and also the topic of the multi-formation tracking. So all these things they are somewhat connected, and therefore the important is that how you are able to control the agent, something like this. So this example for you is the autonomous polishing in the manufacturing. But in fact, it's a high-level technology, so you need to remember that how to make it some sort of differentiate, or how to make a group of the agent, how the agent should work together, or how the agent should do competition. So these are the some topics related to the advanced manufacturing.
Thank you, sir.
Thank you, sir.
With this, we can conclude the forenoon sessions of day 4. I again extend my sincere thanks to respected sir for giving such an informative sessions on the cyber events, H infinity control, multi-agent systems, and their cooperative operations with the help of different advanced control algorithms. Sir has also discussed some initial parts of the model predictive control. And we are extremely thankful to you, sir, for sharing all your experience and informations with all of us. And with this, we are concluding the forenoon sessions now. And the afternoon session will start at 14:30 Indian Standard Time. And I like to announce one more thing to the house, that as a rule of the GYAN course, the evaluations of the participants is a compulsory or mandatory task. So considering this fact, the evaluations of the participants will be conducted on tomorrow on 19 hours IST, and it is requested to all the participants to appear in that evaluations or test so that the certificate of the GYAN course can be provided to them. So it is a compulsory task. So all the participants are required to appear in the quiz test, which is scheduled on tomorrow at 19 hours IST. With this, we are concluding the forenoon sessions now, sir. And thank you once again.
Okay, thank you very much. And I will send you the material if you want to share with the participants.
Yes,
Thank
yes,
you.
sir. Yes, sir. Because the evaluations, the syllabus of the evaluations, we have written till today's lectures. So kindly share your material so that I can share with them, and they will have a sufficient time to prepare themselves for appearing in the quiz test, sir.
Sure, sure. I will do it. Thank you very much. See you tomorrow.
Thank you, sir.
Okay, thank you.
To all the participants, yes, we are closing this meeting and requested to join the afternoon sessions before the time. Thank you again.